So next, finally, uh, we've been prepared to derive the expression of input referred noise for common source and source followers, the same as the OTA. Uh, Now that we can utilize the principal superposition and Thevenin equivalent to simplify the circuit model, effectively derive the voltage gain for inspection. And at first CS stage, there's a voltage gain of GM R01 in parallel with R02. CS amplifier is depicted here. This is V in and this is V out, VDD and VSS, and this is bias. And R01 equals, this is M1 and this is M2 and this is P channel, an inverted common source amplifier, and source drain resistance on resistance R01, differential resistance or derivative resistance, or and the same for R01 and R02, and in parallel ways combination, in parallel combination from looking into V out to AC ground, VDD and ground. And GM is GM1, and this GM. This is resistance looking to the drain divided by resistance looking to the source 1 over GM. And when we explicitly R01 in parallel to output resistance here, and this is ground, this is ground, and this is ground expressly, and this is IN2 squared bar, and this is current noise power IN1 squared bar, and this is this power noise, current power noise, summed up to this V out, and generating the voltage noise V out, Vn out squared bar equals IN2 squared bar plus IN1 squared bar times R01 in parallel R02 squared. This is more in volt squared per hertz, and these are 4 kT gamma times GM1 and 4 kT gamma GM2 for P channel. GM1 is for N channel, and GM2 is for M channel, and so Vn in squared bar equals this divided by voltage gain of Z squared, which is cancelling this, and 4 kT gamma GM1 plus GM2 divided by GM1 squared, which is 4kt. Finally, we got 1 over gm1 plus gm2 divided by gm1 squared, which is for OTA, the similarity, the difference is just the constant factor is double. Like current mirrors two branches is one branch for one branch of 4kt gamma 1 or gm1 plus gm2 divided by gm1 squared. For two branches, this is double than 8 4kt gamma, and this so easy to remember, but derivation is different, but approximation derivation is these one branches and two branches for OTA, current mirror, active current mirror OTA, differential amplitudes, output noise divided by voltage gain, and equals input square bar of OTA. This is for CS. And next, I'd like to check common gate stage input referred noise. Common gate stage is like this. Some impedance RD is there, like textbook, and the voltage bias, cascade biased maybe is there, and this is the input V and VDD. So AC equivalent to calculate output noise or input noise. This time, when I did for common source stage, I neglected input current noise because input impedance very high compared to source resistance RS. Some kind of input amplifier buffer signals the driver having RS source resistance drives the signal, but there's two comparative large source resistance and less input resistance impedance. Then we need to we couldn't neglect the input referred voltage noise, but source resistance of signal driver is much less than input driver, the input resistance. We can neglect the IN squared bar. In this case, but input impedance comparative to 1 over GM of this bias channel MOSFET, so it's very comparatively very small input resistance. We can't neglect the input referred noise as written in this textbook. So we take care of both. We're taking care of both voltage and current noise. Input referred voltage, input referred current noise also. And for voltage noise, we showed input, and this for this case, this is V out, input and V out. and so there's V out noise, Vn out noise squared bar appears, and this is RD. And for input shorted cases, this voltage noise power equals this current times output impedance, output resistance, and this current is where the input resistance, this current equal 4kT over RD current noise power, and this is of course 4kT gamma GM, this GM, and this added to this, and this RD is very small in parallel with RD RO very large, so RO neglected in parallel combination, and this voltage going to 4kT over RD plus 4kT gamma GM times RD squared approximately. And this is output noise, Vn out squared bar, and for getting bar, and V input noise, if there is V input apply to input for input node like this is biased, and this is RD and VDD. This is modulated, and if this is modulated, VGS is modulated, so the Vn is linearly up increase, this is decrease, this decrease is GM Vn in this direction, Vn in, and also this is source is bias larger than VB, so this VBS makes this, if the source is larger, decrease, also decrease, decreasing factor equal GMB, VBS equals VBS, V into source, VB to source is the same, VB and VS is the same, VS is the same, VS is the same, and Vn, if this node is VS moving the and V this is Vn in not Vn sorry, this is VGS, this is VB, and this is G and S, GS, and D to S, this is AC grounded, bias is constant, so ground, source to ground is the same, so this is VGS, or this is just ground to input, like this, inverse this, inverse this, inverse, this is Vn in, and this is Vn in, at last. So, and the same direction of back bias effect and channel effect, noise is transferred with transconductance GM and GMB, so there appears current noise of this sum. So GM plus GMB Vn in squared word is this current times RD squared word is this is current and this is resistance, output resistance, and this is voltage. This voltage, when making input shorted, we can concentrate on input noise voltage, and this if this is input voltage, referred voltage, this noise, output noise produced by this noise is comparative to this output noise. It's the same. This procedure is already run. We ran this procedure already from this book. Say this is Vn1 out in input short case. This is also Vn1 out squared. So equating this Vn in input referred noise of gate common amplifier is RD cancelled and 4kT. This divided by this 4kT RD plus 4kT gamma GM divided by GM plus GMB squared. This is the input referred voltage noise for CG. Okay. And also we know input current. We must know the input current noise, input referred current noise, to open this node for current noise, and rewrite the schematic with open here, and also open channel current noise I and in which is 2, and V out, Vn2 out, as the textbook squared bar is appeared because of this ion in squared bar, and this is equal to Vn2 out squared bar of when our input is open. When input is open, there's no current in and out from the source. Just this current is activated and circulates from within this loop, and Vn this channel current noise and channel noise is circulated in itself, so it never generates output noise. It doesn't contribute to output noise. Just output noise is 4kT RD. Output current noise 4kT RD. This 4kT ID RD is there, just there. 4kT over RD current noise. Oh no. Not current is it's open and there's no current and circulated, and voltage noises appears with from not this, just RD. RD produces voltage noise, of course, which is 4kTR. This is appears from this generates 4kTR. This generates 4kTR. And this 4kTR equals this Vn2 out squared bar. And this is Rn in squared. And this current is this from this. And this is just Rn in squared bar Rd squared equals 4kTR. So input referred current noise of common gate stage equals 4kT over R. This is Rd over Rd, which is just current noise of output load resistance Rd. So load resistance up here is appears to input current noise because not negligible amounts because of small input resistance of maybe considering back gate GM plus 1 over GM plus 1 over GMB. It's very small, so we can't neglect this. But interestingly, this appears generally just the same as RD thermal noise, current noise, 4kT over RD. This is for common gate, and source follower using output voltage gain. Source follower input refers voltage noise is considered, and current input refers current noise also, like the common source amp. Source follower is, this is V in and this is V bias. This is a constant current bias. And this is V out, and input impedance is like almost infinity compared to 1 over GM. So we can neglect the input current noise in this case. And input voltage noise, or input voltage noise, there's input voltage, there's two methods presented in textbook, and one is very useful to applicable to more probably more when we want to be more accurate for the output resistance or voltage gain. But for simplicity, I'd like to regenerate the derivation of noise. So from simple AB voltage divider as voltage divider, GM divided by GM plus GMB of M1, M2 of M1. This is just current and the DC component, and the AC components are AC components appearing conductance of GM and GMB of M1 only. This is approximation because there are output resistance looking from output RO1 and RO2 also, but these are much larger than 1 over GM1 or this, so we can neglect these. And but for simplicity, in this textbook Vn in squared bar appear for M1, and for M2 In out In1 scalar bar is considered, and there are output resistance. Simply output resistance neglected and at first, but there's a RO. Actually, there's RO1 in parallel RO2 there, but we can neglect, and also 1 over GM plus GMB, but this is more small, and this is neglectable, but considering a more accurate representation, we need to add this R1, R2 in parallel with 1 over GM plus GMB. This is tedious long formula, so at first I neglect these and check the representation of input referred noise for the source follower. Source follower is source following Vin. The difference nearly equal to VTH. Now amplifier gain is very small. Source follower is used for low noise amplifiers because the amplifier gain is less than 1, but input referred noise is comparative as common source, common gate, OTAs. We know from this textbook also, and I'm gonna check it, compare comparative input referred noise, but output noise is smaller compared to common source or OTAs. So source followers amplifiers is useful for yes, low noise amplifier. Low noise output is gained. Low noise buffer. As a low noise buffer, we use in many cases source followers. I just like to comment this, and also this text was commented at last. The same example, and this is bias, and from this we have input noise. This is Vn1 and this is In out. Sorry, Vn equal Vn1 squared bar plus this is Vn out squared bar, Vn out squared bar divided by voltage gain of source follower. Like this, we can simplify the calculation in textbook. There are two ways. Just represent I with current noise add up, and sum to multiplied by R out and divided by AB squared, and get input gain. The same input gain is referred voltage is captured. Is gained captured easily, so but this is more simpler. Separate those two, and this is, we know from lemma this is N channel, GM, this is GM, and home. This is input, gate default, channel noise. Gate default most noise equals 4kT gamma divided by GM1. This is this, and this gain is this. Already know from simple Thevenin equivalent voltage divider representation, and neglecting these R01 in parallel R2, very much larger than 1 over GM plus GMB, and V N out square these. This factor is just M2 for M2, this is M for M1, separating for easy calculation even when this factor is considered for accurate calculation of input referred noise. But usually this is large, so neglectable. And different way, usual way is applicable. Okay, it's okay. But this time, I'd like to follow the text method for procedure of textbook, and this is this, and this is for this, times are out. Are out from here is just looking into the here. Where this is current, and looking into here, R out nearly equals approximately 1 over GM and GM plus GMB. Right, the same as always. So and current noise, of course, for N channel of M2 4kT gamma GM2. So this is this, and this is 4kT gamma GM2 divided by sorry. This is current noise, and voltage noise. For voltage we need to this squared multiply and divided by the gain GM over GM plus GMB squared is this. And this parts for M or M2, this cancelled, and this 4kT gamma GM2 divided by this is GM1, and this is GM1 and GM1, GMB1, GMB1, GM1, and this is GM1 squared. So the same, but both GM constant conductance, transconductance for N channel differ from common source, but representation formula is the same. 4kT. Finally, we got this added to this. This is 1 over GM1 plus GM2 of this time N channel, also M2, and GM1 squared N channel. The same. So almost the same value for common source and source forward, input referred. But the output voltage, output noise voltage is this multiplied by voltage gain. And when in case of source forward, this is less than 1, but GMR in parallel to is much larger than. So the output noise actually for common source voltage amplifiers is larger. Even if the input referred noise is calculated the same level. The same geometry of common source amplifier and source follower compared. When compared, source follower is very small noise. So we use this type for low noise amplifier. So finally we got there. But and then decreasing input referred noises for source follower and common source is the same, making for common source amplifier, making p-channel conductance smaller as possible for current meter biasing, and input amplifier's input conductance higher as possible as we can, making both realization leads to lower noise, input noise, or of course output noise. The same as, but for source followers, making bias, also bias current and MOS conductance as small as possible, and for NMOS input as large as possible. The same. The procedure for lessing or for decreasing noise is the same. Approach is the same, but the actual output noise is much less, false, much small false follower. And that's it. That's all. We are almost finishing useful amplifier topologies, and how to derive input referred noise. Input referred noise is fair matrix or fair index, fair value for any amplifiers having different voltage gains. So it's very important. And are there anything I've left behind to say, to talk this time? No. One thing is commented, must be commented, should be commented. I neglect 1/f flicker noise. Flicker noise is modeled to appear in gate voltage noise, and caused by, seems so to be caused by random telegraphic signals noise, caused by the deficiency in the talks, very thin silicon dioxide layer, oxide layer. The electron jumped into the oxides in some decade, and in some period, and back to the channel randomly, and this is integrated to 1/f noise. The noise in proportion of the frequency, high frequency to the frequency high. The higher the frequency, the smaller the noise. So Bode plot is like this: -20 dB per decade, I don't know. Or rare, or because one wave minus 20 dB per decade, linearly decreasing in dB is one wave noise, and we've been considering summer noise, white noise, the noise flat noise, flat band noise, flat noise floor level, floor level noise, and this is said to be corner frequency, or between the one wave and the white noise, thermal noise, resistance or channel of transistors. And usually we take measures for neglecting one wave RTS noise. The measure is said to be, in some cases, CDS, correlated double sampling, or in other cases, chopper amplifier technique, or mainly these two are very famous, and using these techniques we can neglect one wave noise when adequately designed, or less than. We need to care for higher frequency, for higher than corner frequency, and usually amplifier has a cutoff frequency, noise bandwidth is limited, so delta F is like this area, and we need to sum up the total noise, a very restricted area, and low noise ampere is like realized for using these two CDS or chopper amplifying techniques. So I neglect all this, and this textbook neglect in many scenes one wave noise, but sometimes one wave noise is explained, and also explained and put forward to the problems set. So next time, common source follower of one wave noise for common source followers is to be considered on these recordings. So almost all is over for utility. Just sanity check. I'd like to I'd like to feel comfortable with this theme. So 1 over F noise for source follower, to study just a little bit again next, but it's a problem, and there's no solution. Maybe that's all for today. Very long for simple theme.